Picture falling feet first toward a stellar mass black hole. In the final seconds, something strange happens. Your feet begin accelerating faster than your head. Not because something is pulling your feet. The black hole pulls every atom in your body toward the same point, but your feet are closer to that point than your head, and gravity is stronger there. The difference, just a few thousand kilometers in position, creates a force that doesn't exist on any individual atom, but emerges from geometry alone. Your body elongates, your spine stretches, you become a ribbon of matter miles long, still chemically you, but topologically a string. This is spaghettification, and it raises a strange question. How can a difference in position become a force? Once you understand the answer, you'll see this same phantom force sculpting moons, creating rings, and hiding oceans beneath icy worlds. The answer is deceptively simple. Gravity's pull depends on distance. The closer you are to a massive object, the stronger the pull. Every physics student learns this. But what they often miss is the consequence. If different parts of an object are at different distances from a gravitational source, they experience different pulls, and different pulls mean different accelerations. Your feet accelerate faster than your head. That difference, not the gravity itself, but the variation in gravity across space, is what we call a tidal force. Here's the key insight. Tidal forces don't depend on how strong gravity is. They depend on how quickly gravity changes with distance. The Sun's gravity at Earth is about 170 times stronger than the Moon's, but the Moon is so much closer that its gravitational gradient, how fast the pull changes as you move toward or away from it, is actually steeper at Earth's surface. That's why the Moon dominates Earth's ocean tides, not the Sun. Same principle, different scales, counterintuitive result. This one fact, gravity creates a gradient, and that gradient creates differential forces across any extended object, explains everything from why Saturn has rings to why Jupiter's moon Io is the most volcanic body in the solar system, to why a very specific death awaits anyone falling into a black hole. The term spaghettification was popularized by Stephen Hawking in A Brief History of Time, but the physics traces back to Newton. In his Principia, Newton explained ocean tides as differential gravitational pull, the moon tugging harder on Earth's near side than its far side. But Newton was limited to weak gravitational fields. It took general relativity to reveal what happens when tidal forces become extreme. Near a black hole, space-time curves so dramatically that the gravitational gradient becomes lethal. For a stellar mass black hole, say 10 times the mass of the Sun, this gradient kills well before you reach the event horizon. Consider what this means for a human body. Suppose your head is 2 meters higher than your feet. Near a 10 solar mass black hole at roughly 400 kilometers from the center, the difference in gravitational acceleration between your head and feet exceeds 10,000 Gs. Your feet accelerate towards the singularity 10,000 times faster than you'd fall on Earth, while your head accelerates at a measurably slower rate. The difference stretches you like taffy. Muscles tear, bones separate. Eventually, atoms themselves are pulled into elongated streams, funneling towards the singularity in a thread thinner than a human hair, but potentially kilometers long. But here's what makes this strange. In your local reference frame, you're in free fall. Einstein taught us that free fall is indistinguishable from floating in empty space. No sensation of weight, no way to detect gravity locally. Yet you're being stretched apart. The tidal force isn't something you can shield against or counteract. It's not a force in the usual sense. It's a geometric consequence of how distances relate to curvature. Two objects falling together, if separated in space, will accelerate at different rates. That's all a tidal force is. But when the curvature is extreme, drifting apart becomes being torn into atomic streams. Interestingly, supermassive black holes are actually safer, at least initially. Because they're so large, the distance from the event horizon to the center spans millions of kilometers. The gravitational gradient is gentle at the horizon. You could cross into a billion solar mass black hole without noticing anything unusual. The tidal forces only become lethal deep inside. Of course, by then you're causally disconnected from the rest of the universe. A strange consolation. But tidal forces don't just kill. Remember the principle. Gravity varies with distance, and that variation stretches or compresses anything extended through it. Near a black hole, this destroys. But operating more gently across the solar system, the same gradient creates something remarkable: heat. In January 1979, 3 scientists at UC Santa Barbara, Stanton Peele, Patrick Casson, and Ray Reynolds, published a paper with a startling prediction. Jupiter's moon Io, they argued, should be the most volcanically active body in the solar system. Not because of radioactive decay like Earth's interior, not because of recent formation, but because Jupiter's gravity was continuously kneading the moon's interior like bread dough, generating heat through friction. Their timing was remarkable. 2 months later, Voyager 1 flew past Io and photographed active volcanic plumes shooting 200 kilometers into space. The prediction had been confirmed within weeks of publication, one of the most dramatic examples of theoretical physics making a testable prediction and nature immediately saying yes. Here's how it works. Io orbits Jupiter in an elliptical orbit maintained by a gravitational resonance with the moons Europa and Ganymede. As Io moves closer to and farther from Jupiter during each orbit, Jupiter's tidal pull strengthens and weakens. The moon flexes. Its solid rock surface deforms by as much as 100 meters with each orbit. That's Earth's surface rising and falling by the height of a 30-story building every 42 hours. This flexing generates heat through internal friction. Bend a paperclip back and forth rapidly, it gets warm. Same physics scaled up to a world 3,600 kilometers across. The heat is staggering. Io produces roughly 2.5 watts per square meter, 40 times Earth's internal heat flow, enough to melt rock throughout the interior, driving volcanism that resurfaces the entire moon every few thousand years. Io has no impact craters because they're constantly erased by lava. Notice the principle at work again. Gravity varies with distance. When that distance changes cyclically, objects flex. Flexing generates heat. The same physics that stretches you to death near a black hole, operating more gently and repetitively, turns a moon into a volcanic furnace. One orbital step outward, Europa experiences the same tidal flexing, but weaker. Not enough to melt rock, but enough possibly to keep water liquid beneath an icy shell. Measurements from the Galileo spacecraft suggest a global ocean perhaps 100 kilometers deep, containing twice the liquid water of all Earth's oceans combined. The same principle that incinerates Io's surface may maintain a habitable environment beneath Europa's ice, which is why NASA's Europa Clipper mission launched in 2024 to investigate. One gradient, 2 very different outcomes, determined only by distance and intensity. Tidal forces also set boundaries. Get too close to a planet, and the gravitational gradient across a moon exceeds the moon's own self-gravity, the force holding it together. At that point, the moon disintegrates. This boundary is called the Roche limit, calculated by French astronomer Édouard Roche in 1848. Inside the Roche limit, moons cannot survive as coherent bodies, but debris can. Saturn's rings sit precisely inside Saturn's Roche limit. They're not pristine leftovers from the solar system's formation, they're the shredded remains of a moon that ventured too close. The same physics that would spaghettify you near a black hole operating at planetary scales created one of the solar system's most beautiful structures. The gradient also creates torque. The moon's near side experiences slightly stronger gravitational pull from Earth than its far side. Over billions of years, this differential created a subtle braking effect, slowing the moon's rotation until it matched its orbital period. Now, the same hemisphere always faces Earth. This is tidal locking, and it's ubiquitous. Io, Europa, Ganymede, Callisto, all locked to Jupiter. Pluto and Charon are mutually locked, each showing one face to the other forever. Mercury sits in a 3-to-2 resonance, rotating 3 times for every 2 orbits, stabilized by the Sun's tidal pull. Gravity's gradient doesn't just stretch or heat, it synchronizes. So what actually kills you near a black hole isn't the black hole's gravity in any absolute sense, it's the difference in gravity across your body, and that same difference operating throughout the cosmos at varying intensities heats moons into volcanism, melts ice into potential harbors for life, shreds moons into rings, and locks worlds into eternal orientation toward their parent bodies. The opening question now has its answer. How can a difference in position become a force? Because gravity isn't uniform, it falls off with distance, and whenever a gradient exists, a change in something across space, any object extended through that gradient experiences differential effects. It's not that something pulls your feet harder in isolation, it's that space-time curvature varies across your body, and that variation, when you're extended through it, manifests as stretching along the gradient's direction. Einstein formalized this beautifully. What we call gravity is really space-time curvature, and tidal forces are its direct signature. 2 freely falling particles separated in space will drift toward or away from each other purely because of the curvature between them. That relative acceleration is the true face of gravity, more fundamental than the familiar pull felt standing on Earth's surface. The universe is threaded with these invisible gradients. Most of the time, they're too gentle to notice. Earth's ocean tides rise and fall, but humans don't stretch measurably walking around the planet. But approach a dense enough mass or orbit close enough to a giant world, and the gradient becomes the whole story. Volcanoes erupt, moons shatter, bodies elongate into ribbons of matter. All from the simple fact that gravity cares about distance, and distance, somewhere in the universe, is always changing. Like and subscribe, and click the bell icon to be notified when we upload. Thank you for watching.